Okay, today we're going to talk about Chapter 4, which is probability. And in your notes, the first thing it says is rare event rule. It says if under a given assumption the probability of a particular observed event is extremely small, we can conclude that the assumption is probably not correct. Generally, this is less than 5%. What this means is, remember back in Chapter 3, we started doing usual, unusual, and you took the mean and added and subtracted 2 standard deviations. That gave you the usual range. And per the empirical rule, that's 95% of your data. So the other 5% is unusual. In probability, we're always finding a percent, somewhere between 0 and 100%, of the probability of something. So to do usual, unusual, and probability, if it's less than 5%, it's unusual. So probability is new, so we have some new verbiage. You don't have to memorize this, but you have to know it for when they use it in the problems and directions and such. So an event is any collection of results or outcomes of a procedure. A simple event is an outcome or an event that cannot be broken down into simpler components. And sample space for a procedure consisting of all possible simple events. That is, the sample space consists of all outcomes that cannot be broken down any further. So now to say that in English, the event could be you're going to have 2 kids. Okay? Well, there's only 2 outcomes for 2 kids. You're either going to have a boy or a girl. But you could have that different combinations within those 2 kids. You could have 2 boys. You could have a boy, then a girl. You could have a girl, then a boy. Or you could have 2 girls. So in your sample space, you have 4 possibles for having the event of 2 kids. So sometimes sample space is just the total given, and other times it's more complicated, like the boy-girl thing, that we have to think of all the combinations for getting it. A simple way of getting those combinations is with the fundamental counting rule. For a sequence of 2 events in which the first event can occur m ways and the second event can occur n ways, the events together can occur a total of m times n ways. So just like having the kids, if you're having 2 kids, there are 2 possible outcomes each time, boy, girl, boy, girl. So if I multiply 2 times 2, I get those 4 outcomes I outlined on the other one. Boy, 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 girl, girl, boy, and girl, girl. 4 different outcomes. So here's another example like that. Suppose you're going to roll 2 fair 6-sided die. Now, anytime in this book they say dice or die, they're talking about 6-sided dice. And fair just means they're not loaded or anything, that each side has an equal opportunity of coming up each time. If they have a different size dice, like 4-sided or 8-sided, they'll tell you in the problem. So if they just say dice, it's 6-sided dice. So they have 6 sides each. So if we roll 2 of them, and each one has 6 sides, so there's 6 different things that could happen. If you do 6 times 6, you get 36. And here's all the possible 36 ways that it can happen. You could make that table every time, but it's a whole lot easier just to say 6 times 6 is 36. Another example, if a baseball manager has 5 pitchers and 2 catchers, how many different possible pitcher-catcher combinations can he fill? Well, same thing. If I do the 5 pitchers times the 2 catchers, I get 10, so there's 10 possible combinations for pitchers and catchers. This is with a tree diagram. So in a tree diagram, it's like we did with the dice, except instead of listing each way, we put the pitchers and then the possibles beside them, and it shows all 10 different pitcher-catcher combinations. Okay, so here's a couple more examples with that. This is something that should be pretty common to you. You're always having to come up with passcodes for things, like you usually have to get a 4-digit passcode to get in your iPhone or whatever. So the possible numbers of combinations that people can come up with, they figure out with this fundamental counting rule. So like this one, suppose you have a security system for your house that has a 4-digit access code. How many access codes are possible if each digit can only be used once? Well, first off, you got to understand what digits are. Digits are the numbers 0 through 9. So that's 10 different possibilities. If you count on your hands, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, you're holding 10 fingers up. So that's 10 different numbers. So on my first digit, I can use any of the 10 numbers. However, it said I can only use each digit once. So once I use one of them, I can't use it anymore. So next time, I only have 9 choices. And the next time, I only have 8, and then 7. Multiply all those together, and that gives you 5,040 different possible access codes that you could come up with. Okay, so there's a couple more of those examples on your notes. Hit pause, try them yourself, and then hit go to see what the answers are. Okay, so the second one, we still have that 4-digit access code, but this time they say the digits can be used more than once, but the last digit cannot be a 0. So that made the first 3 10s because I can use them more than once, but on that last one I had to take the 0 away, so it made it 9. So 10 times 10 times 10 times 9 is 9,000. Then the last one, same 4-digit access code, but this time they gave me the conditions that the first digit cannot be a 5 or a 7, and the last digit must be odd. So the first digit, if it can't be a 5 or a 7, that's 2 numbers. 10 minus 2 is 8, so it could be 8. I have 8 possibilities for it. There was no conditions for the second or third digit, so they can be any of the numbers, so they could both be 10. The fourth digit can only be odd, so that's 1, 3, 5, 7, or 9, so there's only 5 of those. 8 times 10 times 10 times 5 give you 4,000 possibles. So as you see, the more restrictions you put on it, the less possibilities you have. Okay, law of large numbers. As a procedure is repeated again and again, the relative frequency probability of an event tends to approach the actual probability. This is our first look at how data tends to go to normal distributions if samples are repeated enough. This law of large numbers idea becomes very, very important in Chapter 6 and in statistics in general, because that last statement, we found out that if we can do things over and over again and take different samples and then put together the statistics from those different samples, that statistics turns out to be pretty normal. So that puts everything in the same kind of distribution, and we can make much better guesses with it. What it has to do with probability is, say you were flipping a coin. If I had you flip a coin 10 times and count how many times heads came up, you'd all get different answers. If I had you do it 20 times, you'd still get different answers, but they'd start repeating each other more. If I made you do it 1,000 times, you'd all probably come out with just about a half, because the probability of getting heads when you flip a coin is a half. There's one side that's heads out of the 2 possible sides. And that's how a lot of the things in probability do. If you do them over and over and over again, you'll come out to the actual probability. The way you denote probability, P stands for the probability, ABC is the different events. So P of A denotes the probability of an event occurring. I never actually use ABC like that. I just put whatever it is that I'm trying to find in it. So if I wanted the probability of getting heads when I flip that coin, I would just do probability heads. Now, I do want you always writing that probability notation in front of your answers, because in Chapter 5, it's how you know what to do. So I will ding you on the test if I asked you probability of heads. If you only told me a half, I'd count it. I'd take some points off on you. You got to say probability heads equals 1/2. So make sure you get in the habit of writing this probability part, not just the answer. Some probability limits. Probabilities, I said at the beginning that probabilities go between 0 and 100%. If you take that to a decimal, that's between 0 and 1. You cannot have more than 100% in a probability. You can't have less than 0% in a probability. If it is 0, if you actually get 0 as your probability, that means the event is impossible. It is not going to happen. So that's like the probability of getting a square tire if you went to buy tires. They don't sell square tires. They only sell round tires. So you're never going to get a square tire. So that's a probability of 0. Probability of an event is certain to occur is 1. So 1 is 100%. There is no ifs, ands, or buts. It's going to happen. The probability the sun will come up tomorrow is 100%. For anything in between, it's in between there. It's between 0 and 1. Now, that being given, never ever round to 0 or 1. So if something is 0.000000013, it's not 0. There is very little probability it will happen, but it is not impossible. So when you get something itty bitty like that, so if you have something like 0.0000013, one way we denote that is 0 plus. So if you see a 0 plus in anything, it means it was a tiny, tiny little probability that would round to 0, but we're not allowed to round it to 0. So we put 0 plus to indicate that it's not really 0. Likewise, if you had a probability of 0.99999, those are 9s. They don't look like 9s, but pretend they're 9s. You would not round that to 1. Because even though there's very, very little probability that it won't happen, you don't want to round it to 1 because that makes it an absolute certainty. Let's see if I can make better 9s. There we go. Still not gorgeous, but at least they don't look like some other number now. Okay? So never round to 1, never round to 0. And that's just another thing showing you how values of probabilities relate to each other. And that if it's between 0 and 0.5, it's unlikely. And between 0.5 and 1, it's likely. The closer you get to 1, the more likely it is. The closer you get to 0, the more unlikely it is. Okay, so here is your basic rule for computing probabilities. It's just a fraction. All it is part out a whole. Number of ways A can occur, total outcomes in a sample space. So probability is simply part out a whole. So here's an example. What is the probability of rolling a 3 on a fair 6-sided die? Well, how many ways can you get a 3? 1. There's one side that's a 3. What are your total outcomes in your sample space? 6. There's 6 sides to the dice. So the probability of 3 is 1 over 6. That's it. So however many is possible over total number in your sample space. Okay, so you got 2 more examples there. Try them. Oh, you can't do the last one because you're not in class. What's the probability of choosing a male in this classroom? Well, unless you have a really, really good memory, you're not going to know that one. So just try the next one. What is the probability of rolling an even number on a pair of 6-sided die? Hit pause, then hit go when you're ready to look. Okay, so if you think about even numbers, there's 2, 4, 6, so there's 3 even numbers on a dice. 6 sides on the dice, that's 3 out of 6. And as always with fractions, you always, always, always reduce a fraction. So 3 over 6 equals 1/2. And I'll skip that one. Class I did. I forgot about that slide. I would have deleted it if I'd thought about it. Okay. Complementary events. The complement of event A is denoted by A with a bar over it. Okay? And it consists of all outcomes in which the event A does not occur. Some formulas you want to write down about that. Basically, because they're the only two things that can happen, if you add them up, you get all your probability. So probability of A complement plus probability of A equals 1. And if you know one of them and you want to know the other one, just subtract from 1. So you have an example in your notes. Suppose you roll 1 dice. Find the probability that the die will not land on a 3. Now, that's easy enough to do without complements, but we're going to do it with complements just to illustrate. So first, find the probability that it will land on a 3. Well, that's one side. We did that a while ago. There's 1 3 out of 6, so that's 1 out of 6. So then, that it will not land on a 3 would be the complement of that. So probability not 3 is 1 minus probability of 3. So 1 minus 1 6 equals 5 6. And like I said, that would have been easy enough to figure out ourselves without going through all that subtraction stuff. There's only one side that is a 3, there's 5 that's not, so 5 out of 6, that's easy enough. Better is this one. A recent survey shows that 64% of all third graders bring their lunch to school each day. How many third graders do not bring their lunch to school each day? Well, now that one, there's no way to figure out without just using the complement. So probability no lunch is 1 minus probability that they have lunch, so 1 minus 0.64 or 0.36. 0.64 plus 0.36 adds up to 1. It's your 100%. Now this slide I put in there because there's a lot of people who do not know cards. And probability is used a lot in cards. Drawing a card is a great thing for doing probability. So just to go over a deck of cards in case you don't know it. There are 4 suits in a deck of cards: clubs, diamonds, hearts, spades. And each suit has 13 cards: ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king. The jack, queen, king are called face cards. 2 of the suits are black, the clubs and spades, and 2 of the suits are red, the diamonds and hearts. Okay, we're going to come back to probability in a minute, but I'm going to sidetrack into odds for just a second. The only reason we have odds put in here, I'm pretty sure there's not even a slide on or a question on odds in my stat lab. But the only reason I put odds in here is because people think that odds and probability are the same thing, and they're not. Odds are part to part. The odds in favor of an event is a ratio of the favorable outcomes to the unfavorable outcomes. So in odds, you're comparing the event and its complement. Whereas in probability, you're putting the event over the sample space. So probability has the total, odds is the 2 parts being compared. To give you an actual example of that, suppose there are 12 boys and 10 girls in a classroom. If I wanted to find the probability of choosing a girl, I'd put the 10 girls over the total kids, which is 22, and reduce that to 5/11ths. But the odds of choosing a girl is 10 to 12 or 5 to 6, reducing that. Ratios are fractions, so you can reduce them just like you do fractions. But see, there were 10 girls and 12 not girls. So since I was choosing a girl, I put the girls first and then the not girls or the boys second. If I wanted the odds of choosing a boy, I'd do it the other way. I'd put the 12 first and then the 10, it'd be 6 to 5. But see how odds are part to part, where probability is part to whole. Okay, so there's another example of this with beads. Hit pause, try it yourself, hit go when you're ready to see the answer. So we've got 4 yellow, 5 pink, 3 blue, and 7 white beads in a bag. Find the probability of drawing a blue bead. Well, there are 3 blue beads and 19 beads total, so probability of blue is 3 over 19. Find the probability of drawing a black bead. Well, there are no black beads, so it's impossible to draw a black bead, so that would be 0. Find the odds in favor of drawing a blue bead. Now this is odds, so it's part to part. There are 3 blue beads and 16 other beads, so it would be 3 to 16. Okay, Find the odds against drawing a pink bead. Well, it's against drawing a pink bead, so I have to put the not pink beads first. There are 14 beads that are not pink and 5 beads that are pink, so it's 14 to 5. Find the probability of drawing a bead that is not white. This time it's probability. So since there's 7 white beads, there's 12 not white beads. So that's 12 over the total 19. Find the odds in favor of drawing a blue or a white bead. Well, this is in favor, so I want the blue or white beads first. There's 3 blue, 7 white, so that's 10 blue or white beads. And if I have 10 of those, since there's 19 total, there's 9 that are not blue or white. So 10 to 19. Okay, now we're going to get a little more complicated. We're not happy, because we're curious human beings, we're not happy with just doing simple probability like that. We now want to figure out, well, what if I wanted the probability of this or this? Or what if I wanted the probability of this or that, or and that? What if I want the probability of this given that? So since we have to be more curious, we have to have a few more rules in finding probability. They're all based on that basic probability of part over whole. But now, since we start putting them in different combinations, we have different rules. For the first rule, for the addition rule, we have to first think about, are things disjoint or mutually exclusive? Because if they're disjoint, I find my probability one way, and if they're not, I find it a different way. For 2 events to be disjoint or mutually exclusive, disjoint, mutually exclusive means the same thing. For 2 things to be disjoint, they cannot occur at the same time. So they're complements. So that second set of Venn diagrams there, where you've got probability of A and probability of B, and they don't overlap at all, those are disjoint events. If they overlap, then they are not disjoint. There is some time when they both happen at the same time. So a little example of that. Say event A is randomly selecting a person who's a female student. Event B is randomly selecting a person who works full-time. Event C is randomly selecting a person who is unemployed. Are event A and B disjoint? Well, no. You can be a female student and work full-time. Are events B and C disjoint? Why, yes. You can't be full-time, work full-time, and be unemployed. Not legally, anyway. Okay, so the first one of those rules for the more curious probabilities is the addition rule. The addition rule is a device for finding probabilities that can be expressed as the probability of A or B, which is the probability that either event A occurs or event B occurs, or they both occur, as a single outcome of the procedure. That should be word. The key word in this section is or. If you see or, you should think addition. Underline that. When you see or, you should think addition. Okay, so you have 2 different rules there for the addition rule, and it depends on if it's disjoint or not. If they're disjoint, you just add up the 2 possible probabilities. So the probability of A or B is probability of A plus probability of B. But if they're not disjoint, you add up those 2 probabilities, but then you subtract the overlap. Because remember, the first one was when the 2 circles didn't cross. So I had A and I had B, and it's just 2 individual things. I just add them up. But this one was when the circles did cross. Aren't those gorgeous circles? So you've got A, you've got B, and then you have here where you have A and B. Well, if I added A, I'm adding this. And if I add B, I'm adding this. So I end up adding this little part in the middle twice. So I have to subtract it off once. So if it's not disjoint, you have to subtract where they both happen once because you just added it twice. Okay, so here's an example. Roll a die, and event A is that you roll a 2, and event B is that you roll a 5. Are events A and B disjoint? Why, yes, I can't roll a 2 and a 5 on a die at the same time. So since they're disjoint, I just add up their individual probabilities. The probability of rolling a 2 is 1 out of 6. The probability of rolling a 5 is 1 out of 6. 1 out of 6 plus 1 out of 6 is 2 out of 6, which reduces to 1/3, because you always reduce your fractions. Okay, so here's a little more complicated example. Suppose the YMCA has an enrollment of 4,563. Of this 4,563, 852 play in the basketball league, and 3,041 are male. So, 852 males or females play in the basketball league. And 3,041 of the 4,563 are male. Of the members of the basketball league, 520 are male. So out of that 852, there's 520 males. Are the events selecting a male and selecting a member of the basketball league disjoint? No, because obviously there are males in the basketball league. So when I want to find the probability of male or basketball, I do probability of male and probability of basketball, but I have to subtract off the and. So there are 3,041 males, so the probability male is 3,041 over the total 4,563, plus basketball. Well, there's 852 people that play basketball out of the 4,563. Then males that play basketball are 520, so I subtract off 520 over 4,563, get 3,373 over 4,563. When you start getting crazy big fractions like that, you take it to decimal, because 74% means a whole lot more to me than this crazy fraction. So probabilities can be left as fractions, decimals, or percents. So all of these, let me erase some stuff to make a point. All of these are the correct answer. If you left me the fraction, the decimal, or the percent, it's all correct. I would take any of those. It depends on what we're doing as to which one I would ask for, or what my stat lab will ask for. And like I said, when you've got great big fractions like that, the decimal just makes so much more sense. But all three of those are probability answers. You can answer probability as a fraction, as a decimal, or as a percent. Okay. The next one that we're talking about is dependent and independent, because we're going to change rules. So we did a couple examples of the addition rule. Now we're going to do the multiplication rule. In the multiplication rule, you have to think about whether something's dependent or independent. Two events A and B are independent if the occurrence of one does not affect the probability of the occurrence of the other. They're dependent if the occurrence of one does affect the probability of the occurrence of the other. So, like two events, event A is being 6 feet tall, event B is having blonde hair. Are they independent? Yes. Being 6 foot tall doesn't dictate what color hair you have. Being blonde doesn't designate how tall you are. So those are independent. In the multiplication rule, we have to think about that because we're going to draw 2 cards. Well, at least 2 cards. There could be more than 2. But if we're doing probability of A and B, it's that we're getting A and B. And if by getting A, it changes things so that it affects the probability of getting B, then it's dependent. When you see the word and, you should think multiplication. So here's your 2 rules for that. If A and B are independent, I just straight multiply them, no problem. If they're dependent, I still just straight multiply them. But this and this would, I'm sorry, I'm going to try that again. Somehow I completely missed. Okay? This and this would not be the same numbers. So if they're dependent, when I go to draw B, or get B, it's going to be different than if they were independent. A will be the same, because that's the first one, nothing affected it. B will be, if it's independent, I'll get the probability of B. If it's dependent, I'll get the probability of B given that A has already occurred. Okay, so first we'll do an independent one. Suppose you're going to throw a fair die and flip a coin. Well, whatever I roll on die doesn't affect what I get on a coin, so that's independent. So I just find the two individual probabilities and multiply them. Probability of rolling a 3 is 1 out of 6. Probability of flipping a coin is 1 out of 2. Multiply those together, you get 1/12, which is 8.3%. Okay, this is another independent one, and this is one they love to do. We're finally back to those cards. This is one they love to do for independent, dependent, and it all has to do with this sentence on if you're replacing the card. If I replace the card after I draw it, I'm having the same 52 cards every time, so that makes it independent. So I'm drawing a king and an ace. Well, there's 4 kings, so the probability of drawing a king is 4 out of 52. There's 4 aces, so the probability of drawing an ace is 4 out of 52. Multiply that together and you get 0.59%. But if I don't put the card back without replacement, it is not independent. And what changes is my total number of cards. So my probability of drawing a king is still 4 out of 52, but my probability of drawing an ace now is 4 out of 51. And that changes my probability just slightly. It's 0.6 instead of 0.59. Now, that didn't change enough for me to care. I could have rounded the other one and made it 0.6 as well. The reason it didn't change very much is because I didn't draw enough cards. There's a thing called the 5% that says if a sample is no more than 5% of the population, then you can just treat it as independent anyway. So like the card example, if I did 5% of 52, that's 2.6. So I'd have to draw 3 or more cards before being without replacement would really matter. So since I only drew 2 cards, that's why the probabilities were basically the same. But if I'd have drawn 3, 4, 5 cards, I would have started seeing very much difference between with replacement and without replacement. Okay, so some other cases of probability. At least one is probability of getting at least one of some specified event, and it's easier to do if you think complement. And conditional probability is the probability of event which we have additional information that some other event has already occurred, not individually. So if you see at least one, what you should think is 1 minus none. It is easier, at least one is like all the things that could happen, except when that one thing doesn't happen. So it's usually much easier to figure out if you figure out the one time it doesn't happen and then just subtract it from 1. So for an example, suppose you flip a coin 6 times. Find the probability that in 6 flips you get at least 1 heads. Well, let's think, what is none in this case? Well, none is that I get no heads or all tails. So none would be getting 6 tails. Well, I can do that. That's an and. Tails and tails and tails and tails and tails and tails. So I just need to multiply all those. Well, the probability of getting tails in any given time is 1/2. If I do 1/2 times itself 6 times, that's 1/2 raised to the 6th power, or 1/64. So then, to find the probability at least one heads is 1 minus that 1/64, or 63/64. So instead of figuring out all the different ways to get one heads, I can just figure out the one time that I don't get heads. Then the other one is conditional probability. For conditional probability, you have the formula down there to do the total number of A and B over the total number of A. What happens in conditional probability is I only care about part of it. So say I did a survey about males and females, and then conditional would be something like, what's the probability they're employed given they're males? So I've decided I only care about the males. So I'm only going to look at the males, and I want to know how many are employed. Well, see, that changes your total. So instead of the total males and females that you surveyed, now you're only looking at the total males you surveyed. So your sample space is different. So now we're going to do all these different probabilities using this table right here. So you'll be referring back to this table for all the rest of the questions in your notes. And we're going to go back through all these different kind of probabilities and do using this table and go back over them. First, let's make sure you can read the table. This was a survey that was taken at a local elementary school regarding which physical education activity was preferred. Some students from each grade were surveyed. The results are listed in the contingency table below. Alright, so if I blow this up a little bit where you can see it better. Over here is ages. So there are 29 kindergartners, 35 first grade, 31 second grade, 38 third grade, 38 fourth grade, 41 fifth grade, 212 kids all together. And then it asks their favorite PE activity, and they only allowed them to pick one because there's no headings that are like tug of war and jump rope, so they had to pick one. 46 of these kids said they liked tug of war, 45 said they liked dodgeball, 50 said they liked jump rope, 71 said they liked freeze tag. And if we look individually, if I look at this 5 right here, that is 5 first graders who liked dodgeball. So if you look at anything in the table, it's each of these things. So 5 first graders who liked dodgeball. Okay, so if you want to, hit pause and go through and see how many of these questions you can answer. And then hit go to see what the answers are. Okay, here we go. So here on the table, let me get rid of this. Oh no, it's not going to let me. Bummer. Because I did it before, it's not going to let me. Maybe I can highlight. Let's see if it'll let me highlight. Alright. So this was 4th grade or freeze tag. So if I do 4th grade across through here, and then if I do freeze tag down through here, do you see how this 7 is counted twice? That's what we have to subtract. Because we added up all the 4th grade, got the 38, we added up all the freeze tag, got the 71, but in that I added that 7 twice. So I have to subtract that overlap back off. So let me get back to the slide I was on. I'll hit pause this time so that you don't have to watch me flip through all those slides again. So the first one, what is the probability a student selected at random prefers dodgeball? Well, if you look on your table and go down from dodgeball, there are 45 total kids who like dodgeball. out of the 212 kids. So that was a straight probability. 45 over 212 is 0.212 or 21.2%. Actually. Then what is the probability of students selected at random is in first grade? Well, again, that's a straight probability. If I look across my table, there are 35 first graders out of the 212 I surveyed. So 35 over 212 is 0.165 or 16.5%. Okay, so then I get an or. What is the probability a student selected at random prefers tug of war or jump rope? Okay. If you look at that on the table, tug of war is one column, jump rope is another column. They don't overlap at all. There was, like I said, there's no time that they did both because they had to pick one. So those are disjoint. Since they don't overlap at all and are disjoint, then I just find the individual probabilities. There's 46 that like tug of war out of the 212, 50 that like jump rope out of the 212. Put that together, you get 45.3%. Okay, now here's our first given one. What is the probability a student selected at random prefers tug of war given they are in third grade? Well, like I said, when you have a given one, it changes your total. So see how this is not 212? That's because they were given that they're in third grade, and the total number of third graders was 38. So given changes your total. So then I want to know, out of those 38, how many like tug of war? So if you look at the table and look at tug of war and third grade, you see that there's 13. So there's 13 that like tug of war and are in the third grade. So 13 out of 38 is the probability a student selected at random prefers tug of war given that they are in third grade. Do your math, 34.2%. Okay, so they asked almost the same question, but they turned it around. What is the probability a student selected at random is in third grade given they prefer tug of war? Well, now because you're given they prefer tug of war, that becomes the total. So the total number that like tug of war is 46. It's the same 13 we had before. There's still 13 third graders who like tug of war. What changed was the total down here because it's a different given. Do the math, that's 28.3%. Notice these two things are not equal because you changed the totals. So one given, you flip it around, it's not going to be the same number. Okay, what is the probability a student selected at random is in the fourth grade and prefers freeze tag? Now I told you a while ago that and means multiply. However, in a contingency table, it is already and. So unless you're drawing more than one, you won't actually multiply. So fourth grade and freeze tag, you go from fourth grade, go over to freeze tag, you see that there are 7 kids under freeze tag that are in fourth grade. So this ends up a straight probability, 7 out of the 212, 3.3%. If I can, let's. Okay, another or one. Probability that you're in fourth grade or prefer freeze tag. Well, or in this case is not disjoint, because fourth graders in freeze tag overlap. I'm going to go back to the table a second. Okay, so I'm not 100% sure how this did. You'll have to let me know if it messed up. I'm not sure by going back to that table what I messed up. So I'm just going to keep going from here and then preview it here in a little while and see if it worked. But anyway, because of that overlap between them, when you add these two, so you add the probability of fourth grade, which is 38 out of 212, add the probability of freeze tag, which is 71 over 212, but you got to subtract that 7 that happened twice off once. So you get 0.481 or 48.1%. Okay, and then this one, what is the probability that 2 students selected at random are in kindergarten? Now here is your multiplication thing. And most of the time when you're doing people, you consider them without replacement, basically because people get annoyed if you ask them the same questions over and over again. But I can use that 5% rule, and out of that 212, unless I'm taking 11 people, I can treat this as independent. So I'm just going to do the 29 over 212 twice, multiplying because I'm getting 2 students, so that's kindergarten and kindergarten, and I get 1.9%. Okay, then another given one. What is the probability a student selected at random is in the 5th grade, given that they prefer dodgeball? Well, given that they prefer dodgeball means I have 45, because that's 45 people in dodgeball. Out of that, the ones that were 5th graders is the 14. So 14 over 45 is 0.311 or 31.1%. Okay, that's our last slide. So we'll go over this more in class. Don't worry if it doesn't make a whole lot of sense to you. It doesn't make a whole lot of sense to people when I do this in class either. But we'll go over it some more. Just make sure you've got your notes done so that when I ask for them tomorrow, you can give them to me and get that daily grade. Talk to you later. Bye.